Okay, next problem, what do you think about? Same mass, same spring, so all the conditions are the same as before. We want to extend the spring to y equals negative 15 centimeters. That means we're going to pull it down and then give it a downward velocity of 6 meters per second. So while we're holding it down, we come in overhead and give it a punch. It goes down starting at 6 meters per second. What's the motion? What's going to be the amplitude? What's going to be the maximum velocity, etc. I'll also comment we could easily find the maximum velocity here. 20 radians per second times 10 seconds, that's your omega A, times 10 centimeters. Having found A, we easily find omega A, and that's going to be 200 centimeters per second, 2 meters per second. But of course, we gave it that velocity at the origin, so that's naturally what we expect. Okay, well, anyhow, think about this, and I'll get a board up here and we'll continue. Okay, just writing down the conditions of the problem. I'm not going to read them to you. We want to use energy considerations to analyze this. Now, we can analyze it, as we've seen, using just the equations of motion, the equation of motion, but we can learn something by using energy considerations, and it can actually expedite the solution that we would get from analyzing the equations. Okay, so question is, now what's the total energy? Can you figure out what the total energy of this thing is? Well, you should pause and think about it, but I'm going to say, well, that's the kinetic energy plus the potential energy. So that's 1/2 mv squared plus 1/2 kx squared. And the total energy is unchanging. That is, as the mass oscillates, the total of its kinetic and potential energies doesn't change because we're assuming an ideal spring, an ideal case where there's no non-conservative force involved. The only force being the conservative ideal spring force. So total energy doesn't change. So at the initial instant, total energy is 1/2 times the 5 kilograms times the negative 6 meters per second quantity squared. The meter didn't come out very well. The board kind of stuck on me. Plus 1/2 of the K, which is 2,000 newtons per meter, times our negative 0.15 meter quantity squared. And you'll notice that the 15 centimeters I wrote as 0.15 meters, that was prudent because the initial velocities in meters per second. We want to have consistent units throughout. So 15 centimeters is easy to visualize. 0.15 meters is not hard to visualize, but 15 centimeters is probably conducive to visualizing. But in doing calculations, we want the 0.15 meters. Well, that's equal to what? Should have done this calculation already, but okay, that's going to be 36, and half of that is 18 multiplied by 5, we get 90 kilogram meters squared per second squared. I'll write it out separately. Plus 1,000, that's 0.0225. 1,000 times 0.225 is 225. So if I've done the calculation correctly, that's 225 Newton meters. The units in both cases are joules, kilogram meter squared per second, or Newton meter. And we get 315 joules. Now this is the kinetic energy we've given it, and this is the elastic potential energy, and actually it's 0.0225 and 1,000. I think got my decimal in the wrong place, And it was a good thing because in thinking about the relative kinetic and potential energies, my intuition was that we gave it a pretty good velocity. We didn't displace it that far, but the kinetic energy would be greater than the potential at this point. So made me question my calculation. I was going to check it anyway, but that comes out a little better. So assuming my calculation is correct, and it might not be, if it isn't, you can correct it, we get this for the total energy. Now, how does that help us? Well, total energy equals ½ Ka squared, which equals 1/2 m times the maximum velocity squared. Knowing the total energy, we could calculate the maximum velocity. Since we know K and we know M, we know the total energy, we could solve, we could set this equal to this and solve for amplitude. We can set this equal to this and solve for maximum velocity, never having to get our hands dirty with the equation of motion, although we are going to need ultimately to do that because we have that initial phase angle to worry about, or that theta naught. Okay, well, solving this, we get 1/2 K times, well, 1/2 times 2,000 newtons per meter times A squared equals 112.5 joules. I'm going to write that as Newton meters squared per second squared. So that A is what? Well, half of 2,000 is 1,000. So if we divide both sides by 1,000, we're going to get 0.1125, which is way more significant figures than are appropriate here. And then Newton divided by Newton is going to give us, I'm not liking what I see here. I'm seeing newtons over meters, dividing Newton meters squared per second squared. Oh yeah, okay. That's A squared, sorry. Newtons divide out. Still ending up with meters cubed per second squared there. And I don't like that. Something's wrong, so I'm going to pause and see if I can fix that. Okay, I wrote newtons here when the joule is obviously kilogram meter squared per second squared. Just thinking Newton meters, I've just written newtons, no excuse. Okay, when we do this, yeah, we are dividing by newtons per meter, and that's going to give us like a meter cubed up here. But then we're going to be dividing by newtons, which is a kilogram meter per second squared. The per second squared divides out. The meter divides the meter cubed, leaving us meter squared. We get A then equals plus or minus the square root of 0.1125 meters squared. And that's going to be approximately equal to 0.35 meters. So we're going to have a 0.35 meter amplitude. We don't want to bother calculating Vmax, except in the process maybe of checking the problem. Now, where does that leave us with respect to the equations of motion? Well, we have the amplitude for the equations of motion, and we didn't have to deal with as many equations of that nature. Of course, we had to deal with this equation, but this is a fairly simple equation. The others are not complicated, but this can be an advantage, being able to calculate the amplitude directly. Okay, now in the next clip we're going to fit the info into the equation of motion for this oscillation. You should think that through before you view the next clip.